Greetings, aspiring scientists. Welcome to today's video. So in case you didn't watch my last video, I sort of ran out of time there. I wanted to do quite a lot of practice questions, but the video was already 40 minutes long or more, so I decided to make a separate video here. And in this video, we're just going to do practice of Lewis dot diagrams, Lewis structures. And it does take quite a while because there's essentially an unlimited variation in types of atoms and difficulty of structures that you could possibly go through, but I'll try to go through a good variety of structures that I think are likely to appear on IB exams. So let's get to it and go to my slides. We'll just start right here with the practice slide. So I've got 18 structures I'm going to show you here, but I do want to just quickly go through the rules again of what I recommended, the steps you might want to follow. Okay, so here's an explanation of the steps I recommend. Generally, determine the total number of valence electrons of all atoms. Divide that by 2 to get the number of pairs. Basically, in the structures that we do, we're not going to have any unpaired electrons, so we're either going to have bonding pairs or non-bonding pairs, and that's about it. Next, arrange the nuclei around a central atom. Usually this is the one that is single type and able to form more bonds. So things like carbon, nitrogen are often center. What else? So all of our things in our chemical formula must be bonded together through at least one single bond. Otherwise they would just float away and they wouldn't be part of the molecular formula. So draw one single bond between the central atom and all others if possible. There are some exceptions to this, like hydrogens might be attached to a different atom than the central atom that might be 2 bonds away from the central atom, but in general, you'll sort of get used to which atoms can do that or not. Okay, extra electrons must then fill the shells of outer atoms as lone pairs, but remember no more than 8 electrons per atom. That's the octet rule. If there are still electrons remaining, add them as lone pairs on the central atom. And then check that everything has a full octet. Everything that should have a full octet. If not, consider where double or triple bonds may be appropriate. Okay, then for polyatomic ion Lewis diagrams, if there's a net charge on the ion, those electrons must also be considered when counting valence electrons. So if you have, for example, -1, that's an extra electron, -2, 2 extra electrons. +1 is a missing electron, +2 is 2 missing electrons, and so on. So you have to add or remove those electrons based on what the ion's charge is. There may be multiple structures that you find to work. In reality, only the lowest energy option of all possibilities will exist, and that one is the correct answer on a test. They'll be discussed later. This will be discussed later. It's based on something called the formal charge. So if you try to do the practice questions with me today and you find you got a different structure, but you still felt like you followed all the rules, well, it is possible that different structures can be drawn, but generally I'm going to show the most stable, actual correct answer. And I'm not going to explain how I know that that's the correct answer until a few lessons later when we talk about formal charge. Okay, so practice here. Draw the Lewis structures for BH3 to start, number 1. So we can choose a central atom that is boron that can make 3 bonds generally. It's got 3 valence electrons. But this does mean that boron is unlikely to make an octet, right? If you look at the total electrons that we have here, we've got 3 for boron, and 3, 1 from each hydrogen is 6. 3 pairs. It's impossible to make an octet on boron in this structure. So if that rule needs to be broken, break it. The octet rule is a little bit flexible, much more flexible than other rules when it comes to Lewis structures. So here we have boron with 6 pairs around it, hydrogens with their full helium shell. That's going to be the structure of BH3. You can also draw it just with the line to represent those pairs. That's generally how I'm going to draw the final version of these. Sorry, not be there, H. BH3. Okay. Number 2, BeCl2. Okay, this is another one that's going to break the octet rule. Chlorine's going to hold on to most of its lone pairs that it starts with, and beryllium has these 2 electrons that are able to make bonds, so it's going to make 2 bonds with these chlorines. Chlorine will complete its octet as it should, and beryllium will just have 2 pairs around it. So you can draw that in bond version just like this, but for proper Lewis structures you always have to write the lone pairs on halogens like this. Okay. What's next? CH3+. This is another one where you're going to choose carbon in the center, but it's not going to be able to fill its octet. There's just not enough electrons in this structure. You got 4 valence for carbon and 1 for each hydrogen. So that's 4, 5, 6, 7, and then plus. So we would remove 1 electron, as I mentioned, a rule for polyatomic ions. So carbon normally has 4 electrons to start. I'm just going to immediately remove 1 to account for that plus charge. Then our hydrogens will come in, get their full helium shell. So carbon here is forming 1 less bond than usual. As I mentioned in my previous video, that's a hint that it's going to be positively charged. It's just lost an electron. So CH3+. Not a very common polyatomic ion, very unstable, but I guess can form sometimes from something like CH3I, where the iodine is a leaving group and just leaves that carbon. Okay, so move on to number 4. I'm going to erase these. BCl3. Pretty much the same as some others that we've done. This boron will also not be able to form an octet, but 3 chlorines will come in. Top, left, right. They'll all have full octets with lone pairs. So the final structure will look something like this. Okay, boron can't form an octet. Chlorine will hold on to its electron pairs, the lone pairs being more electronegative. It's not going to give any up to boron. So boron has to have an incomplete octet here, but that does happen sometimes with group 13 and group 12, or sorry, group 2 and group 13. Like we saw with beryllium. Next, number 5. AlCl3. This is basically the same thing. Al is in the same group 13 as boron. So we can have our chlorines come in. So the final structure will look basically the same as I had in the top right there. Just don't forget any of these lone pairs. So aluminum also will not have a full octet. There's not enough electrons to give all the chlorines and the aluminum the octet. So chlorine, being more electronegative, gets the octets instead. Next, number 6, HBr. Should be pretty easy. We'll just have our Br that has 3 lone pairs, 1 unpaired electron, and then a hydrogen will come in here on the left, pair up. So our final structure is just one single bond to Br. Don't forget the lone pairs. Okay, number 702. I think I've showed this on previous slides before, but you can have your O. Got to be at least one bond between O's here. Each one will then have two non-bonding pairs. And then they have an unpaired electron each. So this is unstable, not really a good form. What they would like is an octet, 8 electrons in the valence shells, so they can each share one electron and make another bond here. O2. So OO double bond, and then 2 lone pairs on each oxygen. Not too bad. Okay, I'm going to clear this slide up. Next, number 8, HCN, one of my favorite molecules. So we have some choices here. We got to choose kind of a central atom. I will choose C, because it can form 4 bonds usually. And then just considering how we're going to put these together, we'll just start with a C. I'll form at least one bond with an N. Then that N's going to have a lone pair and 2 other electrons. And then maybe I'll have an H come in on the left, form a single bond there. So this is a start, but it is not that happy. Carbon's got 1, 2, 3, 4, 5, 6 electrons. Nitrogen's got 1, 2, 3, 4, 5, 6. They would like to have 8. So they need to share again with each other. So I think I'll have these 2 share. And these 2 share. Okay, it's kind of hard to see how that's going to end up, but we'll just have a single bond, HC, and then a triple bond. C to N, and N will keep one of its non-bonding pairs. Okay, maybe I can make that a little bit clearer on where that came from. So this pair will go make a triple bond, and so will this one. Okay. So we needed to make those octets. We had electrons that could be shared. That's what you need to do. So final structure for HCN here. Number 9, CH2O. Okay, choose carbon as the central atom. It can form 4 bonds. We'll have at least one bond with oxygen. We'll have a couple bonds with hydrogen. And then we're kind of stuck. So carbon has 7 in the octet, or 7 in the valence shell, and oxygen has 7 as well. We need to share one more pair between both of them. We'll take 1 electron each. So this will end up a double bond with oxygen, and then 2 single bonds with hydrogen. Now carbon has its octet, 2, 4, 6, 8. Oxygen has its octet, 2, 4, 6, 8. That's all good. Alright, number 10, OF2. Not too difficult. Start with your oxygen, 2 lone pairs, 2 non-bonding pairs. A fluorine comes in each position. It has 3 lone pairs. And that's basically it. Just 2 single bonds. Everything's happy. OF2. Okay. Next, we'll clear this slide. Now here's one that always gets people. O3. But this, because it's difficult, does often appear on IB exams. O3. So there's basically only 2 ways that you could think to arrange this. You might think there's some kind of triangle shape. And it is correct to think like that sometimes, especially with carbons or a mixture of carbon and oxygen, but 3 oxygens doing this, turns out the bond angle here of like 60 degrees and the weak oxygen bonds, I think, just doesn't happen. So it's just from sort of prior knowledge, I know that this structure is not going to form a triangle with one bond between each oxygen. So that leaves basically the other option where we've got 3 oxygens in some kind of basically line shape or slightly bent molecule. So let me just draw that with electrons, single electrons first, what that would look like. OO, OO. Middle one needs to have 2 lone pairs. Bottom one, 2 lone pairs, 1 unpaired. Bottom left, 2 lone pairs, 1 unpaired. Okay, so the middle oxygen here is pretty happy. It's got an octet. But the left and the right one only have 7 electrons. That means there's a problem here. This is unlikely to be the structure. So what to do? Well, it's kind of crazy, but I'm going to take one of these lone pairs that's on the central oxygen, and I'm just going to break it up and do some crazy stuff with it. So one of these electrons, I'm going to make a double bond and share with the right oxygen. So double bond. And then there's another electron here that I didn't use from that lone pair. This one, I'm just going to give to the left oxygen, and just fill this empty space. And I'm going to not share it, I'm going to give it. Full transfer of that electron. So that's going to end up giving this oxygen a negative charge. It is not sharing. Okay, so you might say, well, this doesn't make sense. This is now negative, but the original O3 formula up top here doesn't have any charge, right? That's true, and the thing is, when I broke apart that lone pair on the middle oxygen and I gave 1 electron to the bottom left one, now that top oxygen is forming 3 bonds with 1 lone pair. That's 1 more bond than oxygen usually forms, and it's given away an electron. That means the middle oxygen here has a positive charge. Okay, it had to give up an electron there. So overall, this structure still has a charge of 0, net charge 0, which is just like what was in the formula, O3. So here's an example of where you can have areas of high charge inside a molecule, actual charged atoms, but yet have a 0 net charge on the total molecule that you're looking at. This happens somewhat commonly, so you just have to be aware of it. If you feel like you need to shift electrons around, you can, as long as you follow the rules. Basically, first, use all the electrons that you're working with, use all the pairs, and try to fill up everything's octet that can be filled up anyways. So O3, this structure does follow that logic, those rules. So this is the structure of O3. Basically this here, you don't need these brackets. I was just trying to show that there's no charge total on this structure. So you can just draw it like this. Positive charge middle, negative charge left, total charge 0. Okay. Quite a difficult structure. Okay, let's move on. CH3Cl. Again, I'll choose C in the middle. It can form 4 bonds. It's really not that difficult. We'll have 3 hydrogens come in. Doesn't matter where. top, left, bottom, and then a chlorine come in on the right. It has 3 lone pairs. So our final structure will look something like this. CH3Cl. Hydrogens have their helium shell, carbon has octet, chlorine has octet. Okay, 13. N2H4. Here's a bit of a challenge because here there's not going to be a central atom. You'd probably choose nitrogen, but rather than just saying nitrogen is central, there's going to be kind of a central unit here of N-N bond. I'll draw these with electrons first. Okay, so this is sort of going to be our fundamental central unit of this molecule. Now, both of these nitrogens will have lone pairs as well. They'll have next to unpaired electrons. They each had to start with 5 valence. Now they're sharing one of those in the middle to make a single bond, and then the rest will just be filled up with hydrogens that come. Those 4 hydrogens. Okay, that's basically done. So single bond N. Single bonds with H's, and then lone pairs that were not used. So everything's happy. Here the nitrogens have octets. Hydrogens have helium shells. Okay, N2H4, let's go next. NH4 plus. So N, just draw it normally. 5 valence electrons. We'll have our 3 hydrogens come in. Bottom, left, right. Now we need to put one more hydrogen here. So it's going to come in H1 electron, but this structure is NH4+, so I'm going to just remove this electron from H. So it's going to be just H plus with no electrons, and it's going to come in here and just start sharing this pair. So when it does that, it's going to make a covalent single bond. So here, nitrogen is having 4 covalent bonds. It's one more than usual. It's being forced to share its lone pair that it usually has to itself. So it goes from owning to sharing. It goes from having 2 minus charges in that lone pair to sharing 2 between 2 nuclei, meaning it only gets 1 negative charge on average. So this whole structure gets the positive charge that used to be on the hydrogen above when we remove that electron. So this is the structure, and you do need to draw those brackets. Or at least draw the positive charge on the nitrogen in the middle. Okay, number 15 next, NO2 plus. So N looks like this. We'll have maybe an oxygen on each side come in. Two lone pairs, 1 unpaired. So what can be done here? Well, nitrogen is not too happy. It doesn't have an octet. Neither do these oxygens. We also still have a plus charge here. We need to remove an electron somewhere. Where would be the most convenient place to do that? Well, what if I just remove 1 from the nitrogen at the top here? Kick this out and remove it. Then I'll be able to form double bond here and double bond here. So we'll get N double bond O, these oxygens will have octets, so will nitrogen, but nitrogen is forming 4 bonds. That's one more than usual. We've removed an electron from its lone pair at the top there, so it's a positive charge. So I think, as I mentioned in the previous question, you can either draw this like this or in a full set of brackets where we say we don't know exactly where the positive charge is, but this whole ion is positively charged. Okay. So either of these are fine, I think. Next, number 16, I'll clear this slide. OCl-. So we only have 2 atoms here. It's not that important to choose a central one, but we'll have an oxygen, single bond with a chlorine. Chlorine easily fills its octet, making that 1 bond, but oxygen has 7 electrons here in the valence. But remember, this is OCl-, so we get 1 free electron to add into here. And I'll put it right in that empty space. So we will get OCl-. Now this oxygen that received an extra electron is negatively charged now. You can either draw it like this or in the brackets. Like this. Okay, so that's okay. Or this is okay as a structure. Next, 17, NO3-. Might need some decent amount of space for this. So NO3-, N we'll put in the center. It can form more bonds. We'll start by making single bonds with oxygen. Okay, there has to be at least 1 single bond between N and all of these oxygens, so do that. But each oxygen only has 7 valence electrons, right? So something needs to be fixed here. First thing to realize is this is NO3-, right? So we can add an extra electron somewhere. I'm just going to add it right here into an empty space. But that only solves one of a few problems. This nitrogen actually has an extra lone pair I haven't drawn yet here. So nitrogen actually has an octet, 1, 2, 3, 4, 5, 6, 7, 8, but the oxygen on top and bottom left only have 7 electrons around them. So what to do? Well, I'm going to do similar to what I did with ozone. I'm going to take that lone pair of nitrogen that I just drew, and I'm going to break it up. So one of these electrons I'm going to give, not share, but give to this oxygen. The other one I am going to share. I'll share it here and make a double bond with that top oxygen. So you might say, how do you know to do that, or why are you doing that? It's so random. Well, there's no rule says I can't do it, so I'm doing it because I have to shift electrons around to try to make different bonds or charges appear, get everything its octet. So you got to just try things by trial and error if you don't know exactly what to do. But if it seems like you're going in the wrong direction, things are losing their octets, or you're not using all the electrons or using too many electrons, you got to try to start again. Make sure you're following the rules. All the electron pairs must be used, and everything that can get an octet should get it. So if I do what I just did there, I'm going to have a double bond O at the top. I'm going to have an O- on the bottom right. And since I gave an electron, I didn't share, on the left, this is going to be single bond to another O minus. Now, this nitrogen was forced to break apart that lone pair, give one electron, share one electron. The net result of that is that it's forming 4 bonds now. That's one more than usual. That nitrogen has lost an electron, so it's positively charged. So I think that structure is okay. This has a net charge of -1, but if you want to show it in the brackets, you can do that as well. And double bond O, single bond O on each side. This has a charge minus. Okay, so that's also a way to draw the structure. I know it's a little crazy trying to find out where these electrons go, how pairs split up, what gets given, what gets shared. I've just done this hundreds of times, so I kind of know what I'm doing. I've memorized these, as you will if you do them enough. But if you're not there yet, you just got to try things. Try moving electrons around and follow all the rules. Okay. Last one then, NO2 minus. Let me clear this up. So N will be central. It can usually form 3 bonds. 5 valence electrons. We'll have an O come each side. Make a single bond at least, and then consider what we might do. NO2 minus. So we have an extra electron that must go somewhere. I'm just going to give it to an oxygen here and fill in this empty space. So when we start to draw the structure, it's going to look like minus charge on the right where I gave that electron. Now, what else can be done here? Well, oxygen has 7 electrons in the valence on the left. Nitrogen has 7 in the middle. They can share an extra pair to make a double bond. So nitrogen will keep its lone pair. No need to break it up or share it this time. And then we'll have a negatively charged oxygen on the right that has received an extra electron from somewhere. We don't know where, but it has received one. So I think that structure is okay. You can either draw it like that or in the brackets. Sorry, that's supposed to be 2 separate electrons. Lone pair on nitrogen. And oxygen with 3 lone pairs. And then we just say there's somewhere a negative charge on this structure. That's also okay. And that's basically it. Yeah, so we'll stop there for today. Next time we'll get into bond order and maybe Vesper geometry, molecular geometries. Hopefully you see how I do Lewis dot diagrams, followed along with some of my little steps there. I don't do all those little steps every time nowadays because I've done these structures so many times. I skip steps when I can see what's going to happen. But when you're just learning, you probably should do that. And you can do even more. Like in the first examples I showed where I counted all the electrons, counted the pairs, made sure I used them all. That's something you should do if you find yourself making mistakes for sure. So get to practicing. Good luck, and I'll see you guys in the next one. Thanks.